Vikas,
Present, sir.
Vivekanand,
Sir, present, sir.
Yadav,
Yes, sir.
Yuvraj,
Present, sir.
Okay, there are two absentees today, Vijay Raj and Rahul. Okay, so before I get back to the class, I have corrected your quiz 2 answer scripts, also your assignment 2. I have shared assignment 2 answer scripts. Quiz 2, whenever you are coming here, you can get the answer scripts from me. And for the people who have taken online exam, I have sent the answer scripts. So regarding the performance, it's much better, as you know, as I also indicated in the email. Compared to quiz 1, your performance is much better. The class average has increased from 15.9 to 22.3. 22.3 is the class average out of 30, which is very good. So,
Sir, anyone scored 30 marks, sir?
there is no one scored perfect 30 out of 30. The highest mark is scored by Vigneshwaran. 29 is the highest. Good, keep it up. So, overall performance is good. You should maintain this in your end semester exam to get a good grade from the course.
Sure, sir.
So, if you have any questions, I will share the answer key for the quiz 2 questions, whatever I have asked. So, if you have any questions related to quiz 2, you can let me know. So once you see the answer scripts, if there are any error in the corrections, even in the assignment, you can get back to me. Are there any questions related to quiz or assignment?
No, sir.
I will share the answer key for the quiz 2 questions. Okay.
Okay, sir.
Okay, sir.
So one suggestion for the theory questions, as I already told you, that your answers can be brief. Also, when you write the reasoning, logical reasoning, you should not miss the core point. For example, I have asked you to arrange the combustion chambers based on the valve design. Okay, knocking tendency, right, from the least to the most. The core point in T type combustion chamber is the turbulence. Okay, turbulence is very poor. That's the reason compression ratio is only 4, as I discussed in the class. Also, the other one, I-head, which we use currently, is the primary design that I design. The primary advantage is the knocking tendency is poor because you have a high turbulence in I design, whereas in a T design, that's a first kind of design, right? As I said, it's a 4 design. As old as 1904 or so, compression ratio is only 4 in that design, T-type combustion chamber. One of the primary reason is there is no turbulence. The piston is flat, cylinder head is flat, and the charge has to take 2 right-angle turn, appreciable pressure drop, and there is no turbulence. So turbulence will play a significant role in reducing the flame propagation time. There are 2 things with knocking. One is the distance traveled. Second one is time. Time for flame propagation should be considerably low to avoid knocking. If that time has to be reduced, then you need to ensure that there is sufficient turbulence in the combustion chamber. With sufficient turbulence, the flame will move quick. The advantage in having a flame propagating at high velocity is it will quickly consume the N gas. So N gas won't be exposed to auto ignition conditions for a longer time. So whenever you are asked a question about knocking in SI engine, you should always remember the mechanism. Mechanism is self-ignition of N gas. Okay, so self-ignition of N gas happens because of higher temperature and the exposure time of the N gas to that higher temperature. The temperature may be high, but if the exposure time is less, N gas won't auto-ignite. So turbulence will play a significant role. I see most of you in the assignment, when you arrange the combustion chamber, that point is missed out. Turbulence in the T type and I head type and T head type, it is just opposite. T head, there is nothing. I head, there is appreciable turbulence. Many of you, I'm surprised to see that many of you didn't write that, because that is one of the most important factor. Surprisingly, many of you didn't write about it. Also in a CA engine, when you talk about knocking in diesel engine or CA engine, knocking is primarily due to long ignition delay. So any factor that increases ignition delay is going to increase the knocking tendency, because longer the delay, more the fuel you are injecting, more the fuel that is pre-mixed during the delay. Okay, and following delay, you have instantaneous combustion, that is pre-mixed combustion. That will be more intense. More intense pre-mixed combustion is what is leading to knocking. And that is primarily caused by a longer delay. So any factor that increases delay time, ignition delay time, is going to result in knocking. Okay. So why I am saying all this is, when theory questions are asked, when there is a logical reasoning based question, you should not miss out the primary point, primary aspect, right? Whatever you write other than the primary aspect doesn't carry much significance. So the primary factor or primary cause weightage will be given more. Okay. Did you get what I'm saying?
Understood, sir.
Yeah, you should not miss out the main point there. Okay. So when you write, there may be some additional points, okay, which may not have a significant impact. Whatever factor that is given priority when you write logical reasoning or theory-based questions.
Just to clarify from our end, sir, I think majorly we were focused on the surface to volume ratio when it came to the combustion chamber design. I think that is the reason why we forgot about the turbulence aspect.
In SA engine, turbulence and flame, see, overall combustion is flame propagation based combustion. The rate at which the flame moves will play a primary role in avoiding knocking. Burn rate is governed by flame movement, right? Flame velocity. And higher the flame velocity, more quickly it will reach the end gas location.
Noted, sir. Yes.
Okay. Yeah, anything else related to quiz or assignment? Any other question?
Sir, just one question from my end. That two graphs that you had asked, one for the full load condition and one for no load condition for the heat release profile.
Yeah.
That graphs also you will be sharing as part of your solution, right?
Yeah, yes.
Okay.
The thing, again, the surprising thing with that question is full load and idle. The primary difference will come in the ignition delay time. Okay. Because full load and idle, at the time of fuel injection, in-cylinder pressure and temperature conditions are completely different. At low load or idle, you are just starting. Okay. Vehicle is not even moving. That is idle. So you are just starting the vehicle. Okay. Engine is running, but there is no power in the wheel. Brake power is zero, but engine is running. So it means it's developing power in the cylinder. All the power has been utilized to overcome its own losses. That is what is idle condition. So at idle, you are just starting the engine. So when you spray fuel, the pressure and temperature inside the cylinder will be considerably low. Considerably low pressure and temperature will result in a long delay time. Right? This is the main point you need to capture. At full load, how will you go to full load? You will take the engine to full load gradually, right? So you start increasing the fuel mass, and the mass burnt is high. The temperature in the cylinder will be high. The time when you spray the fuel inside the cylinder, you will have high pressure, high temperature. So the delay time, ignition delay time, is going to be shorter. So what is happening with respect to delay time? At idle, it's considerably high. At full load, it's considerably less. But the fuel mass you are injecting at full load is considerably high compared to idle. These are the changes. Now, when ignition delay time is different, the subsequent phases of combustion, premix and diffusion, are dependent on the delay time. Longer the delay, you will have more intense premix, less diffusion. So that profile change you have to indicate. Okay, that is very important to show. There will be change in the profile at idle and full load, because the first stage delay time is considerably different. That is an important point. Second important point I see few of you missed is, when you inject the fuel, spray the fuel, it's a liquid phase fuel. it should get converted to gas phase. So fuel is absorbing latent heat from air. Because of that, there will be dip in the heat release. I have already discussed that in the class. The dip in the heat release, many of you have missed it. You have directly drawn the heat release from 0 point, which is incorrect. You have to show a negative heat release, then change it to positive, meaning there is a slope changeover point. I even indicated that as one of the criteria being used for start of combustion.
Thank you, sir. Just one additional clarification from my end. Can you just tell a little bit about that heat release in idle condition alone?
Heat release in idle condition. Heat release in idle condition will have a long ignition delay time. Long ignition delay time because when you spray the fuel inside the cylinder, pressure and temperature are less at idle. Since pressure and temperature are less, it will take a longer delay. Ignition delay duration will be longer.
Okay.
So what I mean to convey here is, so this is delay time, ignition delay time. So this is going to be higher at idle. Okay, since this is higher, this is premix phase.
Yeah, more intense.
So this will be high and diffusion will be nothing because at low load or idle, you have a very less m.f. Total fuel injected is considerably less, and most of that fuel will be injected during delay time. In fact, the diffusion phase, sometimes it may not even be visible. Okay, it looks mostly a premix phase of combustion at idle condition, right? This is an important change. Whereas if you look at full load, delay will be considerably short. Because of that, premix will be less, but there will be considerably high diffusion. So it's a diffusion dominated combustion. So this is theta and this is heat release rate. So you could see that the delay time is considerably less. This will reflect in premix phase. Okay, this will also reflect in diffusion phase. So here diffusion phase is nothing. It's considerably less. Whereas here it is considerably high. Whereas ignition delay is considerably low here. It is considerably high in the idle condition. And m.f at full load is considerably high. So this is full load. You know you are controlling load in a diesel engine based on m.f. So you need to inject more fuel here. You are injecting less fuel at idle. Okay. So you see these are the important changes. M.f is high. ID ignition delay is less. Premix is less. Here premix is more. Here premix is less. Since m.f is considerably high, diffusion is considerably higher in the full load. All these changes you need to indicate in your response.
Thank you, sir. So that premix phase in the second graph for the full load will have a higher theta. Also, the peak will have been more in the Z also, correct? Meaning the HRR is higher for full load.
Diffusion you can show only in terms of primarily duration. Okay, so it's a gradual progress. You won't see any abrupt peak or very high peak. Okay, peak will generally be visible in premix phase. Right?
Yes, sir.
So this will be here also. It depends on how much is the delay time. Okay, this is an approximate representation.
Okay,
so I'm not
peak...
worried about showing whether this will be high or the peak in diffusion is high. In fact, there is nothing called a high peak in diffusion. So these two trends are dependent on the value of ignition delay time. But what is more important to show is this long diffusion.
Noted, sir. Noted. Thank you. Thank you. I had some misunderstanding.
So here you could see that short diffusion. I'm rounding it off. So this is diffusion, which is nothing. Whereas in full load, this is a diffusion which is considerably high. You need to show this change, which is very important.
Yes, sir. Clear. Thank you.
Okay. Anything else? Okay. Okay, so let me get started with where I left in the previous class. So we are here now. We are discussing the pollutant formation mechanism in this chapter 5. Okay, so chapter 5 deals with understanding the sources for pollutant, and before that we discuss the primary pollutant types. There are 4 primary pollutant, and these are creating health effects. We briefly discussed about that also. After that, we are discussing the sources and the mechanism. Right after discussing sources and mechanism, we are going to discuss about the factors, engine design and operating factors that affect this primary pollutant formation. Okay, so before that, we are in the last part of this pollutant formation mechanism. So far here, we discussed about NOx formation mechanism, both NO and NO2, which is kinetically driven process. Okay, we discussed Zeldovich mechanism. And the NO once formed, it will get oxidized to NO2. So it's a kinetically driven process, NOx, which is one of the important primary pollutant, especially in diesel engine. It's one of the important pollutant that needs to be controlled. Apart from that, we discuss about the mechanism upon which CO is formed. Okay, when we talk about CO, there is a formation mechanism, there is a oxidation mechanism. Out of total CO formed in the cylinder, some get oxidized in the cylinder itself. So the net CO that comes out in the tailpipe is a resultant of formation rate of CO, and out of which oxidation, a fraction of that, in fact, considerable fraction of that will get oxidized in the cylinder itself. The remaining CO is what is appearing in the tailpipe, and then it is let out into atmosphere. So we discuss the formation and oxidation mechanism of CO. And CO is also a kinetically driven process. So that species formation and oxidation is kinetically driven. Right after that, we started our discussion on HC. Unlike NOx and CO, HC is boundary layer fluid dynamic. SC is governed by boundary layer fluid dynamic, how the flow happens in the boundaries of crevices, how the flow or fuel get absorbed in lubricating oil or in carbon deposit. That's what is primarily affecting the HC formation. So we discussed how HC formation is taking place in SI engine. And in the last class, I have just stopped when we discuss about the HC mechanism, formation mechanism in CA engine. Okay, so I will continue that here. In a diesel engine, CA engine, the HC formation is governed by 4 important mechanisms, and overall all these are coming under boundary layer fluid dynamics. So whatever happens in the boundaries of the combustion chamber, how the flow happens in the boundaries of the combustion chamber is affecting HC formation. And apart from boundary layer dynamics, in the CI engine, since you have a heterogeneous mixture, okay, and the mixture proportion, fuel proportion continuously varies with respect to time and location inside the cylinder. So we discuss about phi local, and there is a phi global. This carries a lot of significance in diesel engine, unlike SI engine, okay, because you have a heterogeneous mixture. This local phi keep on changing, and it's a function of space, that is location inside the engine combustion chamber. It's also a function of time. In terms of crank angle, we analyze combustion process. We already discussed in the first module. So in terms of space and theta, the phi local value is going to be highly variable, okay, in a diesel engine. Because of this, mixing related HC formation also takes place apart from boundary layer dynamics. So there is a over mixing based HC formation. Over mixing, when I talk about over mixing, you are actually adding too much of air to the fuel pocket. We generally analyze combustion when we model CA or diesel engine combustion. We say that we model combustion even in terms of fuel spray pocket. So when you have a fuel and air mixed to a particular proportion, in that mixture, you have one particular phi local value. When you keep on adding more and more air to that mixture, what will happen is that mixture will become too lean. Too lean. When I say too lean, it is below the lean flammability limit. You know, you can ignite only within a range. Okay, there is something called Phi ignitable range, and this Phi ignitable range is a strong function of the type of fuel that you use, pressure and temperature conditions inside the cylinder. Considering that only a certain range of Phi you can burn in the engine cylinder, there are chances that since you have a heterogeneous mixture in CA engine, there are chances that you create over mixing, meaning you are producing Phi which is too lean to ignite. Okay, this is what is happening because of over mixing. Over mixing generally happens during the ignition delay time. That is the first stage of CA engine combustion. In the last class, we discussed about something called the lean flame blowout region, which is created around the spray. Right. So when you spray the fuel at the outer periphery, the film will break. Atomization happens because of air shear force, and then once the film breaks, form drops, air will entrain, and fuel will absorb heat, latent heat from air, gets vaporized, mixed with air in a finite proportion. So near the spray boundary, you will have Phi1 region, which is stoichiometric region, which is ignitable. When you move in a radial direction, that is in this direction, when you move from Phi equal to 1, you could see that the Phi drops. Okay, the Phi is going to drop when you move in this direction because you have a Phi1 region. Phi1 region that is outer, just outside the spray boundary, you have Phi1 region as indicated here. When you move in a radial direction, you have more air available in the surrounding. So more and more air will go and mix with the fuel pocket. Because of that, the Phi will drop in a radial direction. So at the outermost boundary, you will have only air. Only air means Phi value will be 0, right? Nearer to that Phi equal to 0 region, you have Phi much lower than 1, typically around 0.3, which is a lean limit for the mixture, hydrocarbon air mixture. Lean, when I say lean limit, when you reaches this limit, the mixture may not be able to bond, but it can only oxidize slowly. Okay, there is only slow oxidation, there is no burning. Burning is complete oxidation. So it's a kind of partial oxidation of fuel air mixture. That's what is happening in the shaded region. That region is called lean flame blowout region. So it will slowly oxidize, and eventually that partially oxidized hydrocarbon is an emission, unburnt emission from the diesel engine. So this is what is happening during the delay time, ignition delay time. So any factor that increases ignition delay duration is going to increase the over mixing, is going to increase the HC emission. That's why in just now we discussed that at idle you will have a long delay. So can we expect more HC formation at idle condition?
Yes, sir.
Yes, sir.
Yeah. So this is a function of ignition delay time. When you have a more delay time, you can expect that the width of the lean flame blowout region is also increasing. Width. Okay, so you will have a larger width because you are having a longer delay. When delay time is more, then more and more air will entrain and make this mixture too lean. So the width will increase. So width is a function of width of the lean flame blowout region is a strong function of the total ignition delay time. Right, anything that increases ignition delay time is going to increase its lean flame blowout region. So you can expect that the HC emission will be higher when the width of the lean flame blowout region is more. Okay, this is what is happening due to over mixing, and the time at which the over mixing happens in the engine operating period is ignition delay. That is the first stage of CA engine combustion. The other process related to mixing that causes HC emission is under mixing. This is just opposite to what we have discussed just now. There are regions in the combustion chamber where you will have very less air and too much of fuel vapor. Okay, this is what is referred to as under mixing, meaning you are not adding more air to the fuel pocket, which is rich. That's why it is called under mixing. You are not adding more air to the fuel pocket, which is rich. So under mixing will create too rich mixture. When I say too rich, it is above the rich flammability limit. There is a lean limit, there is a rich limit. So there is a Phi rich limit. What it will do is this rich mixture, you have more fuel, you have very little air. Because of this, only partial oxidation of this mixture will happen. This mixture won't completely oxidize and burn. There is no burning here. It's only partial oxidation. So this partial oxidation of too rich mixture is another cause for concern in terms of HC emission, because this is This is creating a partially oxidized hydrocarbon that will leave the engine exhaust in the form of unburnt emission. So you are actually creating too rich mixture that is difficult to burn, and this undermixing happens during the diffusion phase combustion of engine operating cycle. So that is the third stage. After ignition delay, there is a premix stage and there is a diffusion stage. During diffusion stage, you can expect more undermixing, more rich mixture pockets, okay, inside the cylinder. That is going to increase the HC emissions from the diesel engine. The third mechanism is impingement of the spray.
Sir, can I ask one question if you allow, please?
Yeah. Yes.
Sir, what is the mechanism that undermixing will be very prominent in the diffusion phase?
Undermixing is prominent in the diffusion phase. Can you repeat your question?
What is the mechanism of that? So, what is the reason behind that? What is
Okay, so reason behind that is diffusion phase is a combustion period where you have limited mixing time. Ignition delay is a pre-mixing time. Okay, you give more time because that is happening even before the start of combustion. So you have some, that's why we use the word pre-mixing. Pre-mixing means mixing that happens before start of combustion. Diffusion phase combustion is happening after the start of combustion, right? So you are spraying fuel, already combustion gets started. There is no pre-mixing here.
I want to say that the time required for mixing is even lesser compared to pre-mix phase.
That is what is exactly happening. That is what is the cause of concern here. The time available for mixing is nothing here. So as soon as you inject, the fuel has to find the required oxygen, right? Meaning it should be mixed in the ignitable proportion as soon as you inject. That is what is expected during the diffusion phase combustion. And this results in too rich mixture inside the engine cylinder. In fact, during this period, only soot also forms. I will talk about the mechanism. That's the next topic we are going to discuss. Soot formation, which is an important component in the particulate, that also happens during this diffusion phase combustion. Because this is a period where there is no time available for pre-mixing.
Clear, sir. Thank you so much, sir.
That's why you have a rich mixture here. When you have pre-mixing, you have another problem. I said over-mixing. Okay, opposite effect will be happening during diffusion because there is no time for mixing.
Clear, sir. Thank you so much, sir.
Okay, so the other part of mechanism is fuel spray impingement on the cylinder wall. This is causing HC formation in a diesel engine. I think we have briefly discussed about this earlier. When you spray fuel, the fuel may go all the way and hit the cylinder wall, okay, liner region, cylinder wall or liner region. Then the pressure is high. There are two reasons for this. One, injection pressure too high. Second one, the bore, cylinder bore is less. So when you have a small bore diesel engine, you should optimize injection pressure carefully. You should not inject it with a very high pressure value. The combination of high pressure and small bore, this is the worst combination in terms of spray wall impingement, because the tendency or probability of spray wall impingement is very high when you have a high injection pressure and when you have a small bore diesel engine. Okay, so what will happen, this wall or the liner region is the coolest region in the combustion chamber. The temperature here is considerably low because just outside the wall region, you are circulating coolant, right? Just outside the cylinder wall, you will have cooling water jacket. Through the cooling water jacket, coolant flow is taking place. Okay, because of the coolant flow, this wall region is always maintained at a much lower temperature than the rest of the cylinder. So you will have a temperature distribution in the core region. This is called core region, axis region. Here it will be considerably high. When you move in this direction, the temperature is going to drop. In the wall, it's the least. In the core, it is the maximum, because that is where the primary combustion event is happening. You will have a very high temperature here. You will have a very low temperature at the boundary. So wall is the region where the temperature is considerably low. And the problem when you inject fuel and when the spray go and hit the wall, the primary concern here is it is going to form a film. When I say film, it is continuous. We just now discuss about the breakup mechanism. When you have a spray in the core region, air is offering resistance. Because of the air resistance or shear force offered by the air, the film will break. You should not have continuous film. You should quickly break this and atomize. Okay, form drops, start to form drop. That is what is atomization. Film should break, drop should form. That is what is atomization. This atomization is quicker in the core region. But when you create a film in the wall, how do you create atomization, right? So you have a boundary and the film is impinged and you have a lower temperature. So air is not, the access for air is very limited, right? That is one reason. Second reason, you have a lower temperature. So breaking this continuous film into drops and vaporizing it will take considerably a longer period of time. So this film is going to take a longer period of time for its vaporization. This is where I have a problem. You know, you have a limited cycle time, engine cycle time, and vaporization should be done as quickly as possible. When the film takes longer time for vaporization, then it is definitely going to miss the primary combustion event. This is what is happening with the spray impingement on the wall. The fuel impinged on the wall is going to miss the primary combustion. When it will burn in the subsequent cycle. So it will take considerably longer time for its vaporization. It may burn in the subsequent cycle, but the probability of this vapor going along with the exhaust during the exhaust period is considerably high. Thus, this is one of the important source for HESI emitted from diesel engine. So this vapor will slowly leave along with the exhaust gas because of its slow vaporization. Okay, the primary source is high injection pressure, small bore. So you need to carefully optimize your injection pressure in such a way that the spray is not reaching the boundary. Not only pressure and diameter, you should also orient your spray in such a way that you are directing your spray towards the bowl region. I hope you are getting what I am saying. So you should design in such a way that the spray is taken in by the bowl, piston bowl, right? So you should direct it towards the bowl. If at all it goes, it should go somewhat wider, but not too much wide, wherein it goes all the way and hit the wall, which is what is the concern for HESI emission. The fourth source that is listed out here that forms SC is the fuel that enters into engine cylinder from a nozzle sac volume. We have earlier discussed briefly about the sac volume. The sac volume you cannot eliminate in the injector. Any injector will have sac volume. What is the purpose of having the sac volume? Sac volume is a small volume that is available in the end of the injector. Okay. Where the needle, so this is injector needle. This is nozzle sac volume. This needle sits in the sac volume, and whenever the pressure of the fuel is high, the needle will lift, and that is how you spray. And you have orifices in the sac volume through which you spray. When the needle lifts, it opens up the high pressure line to the cylinder, and through that fuel flows and leaves through the orifice as a spray. So why do we need the sac volume? I already discussed about this.
Heat loss, sir.
Not for heat loss. What is the purpose of having this sac volume?
So there are multiple holes in the nozzle because depending on engine design, we may require maybe 3 or 4 or 5 holes or maybe 7 holes. So basically, to have that hole, so you have a surface area which is available. So for that purpose, the sac volume is created over there.
Anything else? Any other purpose? Right, there are 3 important purposes here. One, it allows the needle to sit and remain closed, right? Only when the needle is lifted during a normal operation, the needle is in a closed position. Only when you send the high pressure fuel to this line at appropriate time, the needle is lifted. Either this actuation is either mechanical or electronic, right? In CRDI, it's electronic system. Whereas in off-road diesel engines, right, small low-cost engine, you will have a mechanical actuation. Mechanical actuation is in terms of spring load, right? So you create pressure with a spring, and its stiffness, right? Once the fuel overcomes the spring pressure, the needle is going to lift. This is mechanical actuation. In a common rail system, you are actually energizing a solenoid and allowing the needle to lift because of you create the lift force by energizing a solenoid. The needle is surrounded with the solenoid coil, or you energize externally that coil and that create the required lift force for the needle. Whereas in a mechanical system, you create you are actually creating that required force by mechanical means, right, through a spring. So, but either way, the needle sits in a sac volume, right? It provides a surface for the needle to get seated in a normal position, closed position, right? Only when at the appropriate time, the needle will lift and spray fuel. The second important purpose is you have to measure orifices. You will have n number of orifices. So you need a surface to measure these holes, micron. This orifices generally will be in micron size. Okay, 10 power minus 6 meter. So you will have n number of orifices evenly measured around the circumference. So it provides a surface for measuring orifices, second purpose. The third important purpose is, injector needle is fixed in the cylinder head, and cylinder head is at a higher temperature. So injector is exposed to high temperature hot gases. Some amount of fuel collected in the sac volume will reduce the injector tip temperature. Okay, it increases the durability of the fuel injector, because you collect some fuel in the sac volume and that act as a coolant for the needle. I think in chapter 1 we already discussed that your measuring surfaces or clearances or tolerances in injector is so close, fuel should act as a lubricant. That's why we studied lubricity aspect. Lubricity is one of the property, especially for diesel engine, because we deal with high pressure injection system. So the sac volume will also increase the durability of the injector, because injector tip fuel collected in the sac volume will help in keeping the injector tip at a required controlled temperature rather than very high temperature, which will cause injector tip failure and injector failure. So these are the purposes for having sac volume. But the problem happening because of the sac volume in terms of SC emission is, once the needle sits, okay, the high pressure line is closed. When the high pressure line is closed, since you have a small volume here, some quantity of fuel will get collected in the sac volume. Right? When the fuel get collected in the sac volume, can you tell me how it will create SC emission?
It will drip, sir. It will, because once the
Yes.
nozzle
So
is
since
centered,
the line, high pressure line, when the needle is in the upward position, it is connected to the high pressure line. So fuel is going to be sprayed at higher pressure. But once the needle sits in its position, once the needle closes the high pressure line, there is no high pressure here, but there is some volume of fuel collected in the sac volume. Since the high pressure is lost, the fuel collected here is going to drip, something like this. It's not going to be penetrating into engine cylinder at high velocity. So you need a high relative velocity to create the mixing. The fuel should leave and enter into the cylinder at high velocity. The air should be at a high velocity. So the relative velocity between air and fuel is what is causing the mixing. But since you lose the high pressure, once the needle sits in its place, the fuel collected in the sac volume is going to drip. We use the word drips. It drips out through the orifices at a very low velocity. Very low velocity. And you can think of how this fuel pocket that enters into cylinder, and this happens after the injection process stopped, right? Once a high pressure injection line is closed, the fuel collected here will slowly enter into engine cylinder during later part of expansion stroke. So later part of expansion stroke, already the temperature in the cylinder is less, and you have a liquid phase fuel entering into cylinder, where you have a drop in pressure, drop in temperature. Okay. So this fuel entering into cylinder at very low velocity is going to mix with air slowly, primarily because the mixing is poor due to low velocity of this fuel entering into engine cylinder. Okay, so it mixes slowly with air. Because of this slow mixing, okay, you run out of time. And thereby only this slow oxidation of this fuel will happen. Once mixing is poor, vaporization is going to take longer time. Once vaporization takes longer time, until it reaches its free ignitable range, it is not going to burn. So there is only slow oxidation of this fuel pocket that enters later into combustion chamber, and thus it becomes one of the source for SC formation in a diesel engine. The fuel collected in the sac volume that enters slowly into engine cylinder is a cause of concern in terms of SC emission, because the mixing is poor. So you can expect that there are more fee-rich region because of this mixing is poor. So you can say that this fuel pocket will result in undermixing. Fuel that collected in the nozzle sac volume entering into engine cylinder at low velocity will create undermixing because it cannot effectively mix with air. So there will be too rich mixture because of this, and that will become a source for HSE formation in diesel engine. Clear?
Clear, sir.
Fine. So now we have moved to the last one, primary pollutant, particulate. So we are going to see the mechanism upon which this particulate matter is formed in a engine. So particulate matter, you know, it forms only in diesel engine or CA engine. In SI, there is no particulate emissions. Conventional SI engine, spark ignited engine. Of course, recent development in SI engine is GDI. I think you may be aware of this. So GDI is similar to CA engine, wherein you have a direct injection system. Instead of a port injection system, you spray fuel directly into engine cylinder. When you spray fuel directly into engine cylinder, the problem is the mixing time reduces, similar to CA engine. Although we have early injection in GDI compared to conventional CA engine, still you have a limited mixing time that will cause particulate formation in SI also. So GDI based SI engine will have particulate emission. Conventional port injected SI engine won't have particulate emission. But particulate, when we talk about particulate, it's a major concern only in CA engine, not in SI engine. Okay, because of heterogeneous mixture. Now let us look at the mechanism upon which the particulate matter is formed. Particulate matter is also called simply, you can refer it as particulate. Particulate matter or particulates, both convey the same meaning. Okay, so this, what are these particulate? First of all, these particulates are tiny particles, solid as well as liquid particle. I think I already told you that particulate matter exist in all three states of matter: solid phase, which is soot; liquid phase, which is unburned or partially burned fuel and lubricating oil, is a liquid particle. You will also ask gas phase species like SO2, NO2. All this put together is a particulate matter. So you have this particulate matter existing in all three states of matter. And this is one of the most complex pollutant emitted by an IC engine. And the other problem with the particulate is not well characterized even today, meaning we don't know the exact composition of particulate matter even today. With the available analytical techniques, we have come up with the composition of particulate matter, but people are not very sure about all the constituents of particulate matter. That's why I say that it's one of the most complex pollutant emitted from IC engine for two reasons. One, it exists in all three states of matter. Second important reason is we don't know the exact constituent of this particulate matter. So, so in terms of simple definition, you can say that these are tiny solid or liquid particle which are suspended in a gas stream. So you have a gas stream carrying solid and liquid particle, suspended solid and liquid particle, and all put together is a particulate matter. So when we talk about particulate matter, we are always interested to know the size because it exists in different sizes. Since it's a matter, okay, solid matter also, it exists in different sizes. So this is a typical size range of particulate emitted from diesel engines, 10 nanometer to 100 micrometer. Based on the size, you have three categories or three types of particulate matter. One is TPM. TPM is total particulate matter with the upper size limit of 100 micrometer. So typical size range of TPM is from 10 micrometer to 100 micrometer. 10 to 100 micrometer particles are designated as total particulate matter. Second one is PM10. Anything below 10 micrometer, that is anything from 2.5 micrometer to 10 micrometer are designated as PM10 particulates. The third category is PM2.5. PM2.5 are the particulate matter with size less than 2.5 micrometer. These are very small particle among the three cases. Unfortunately, more than 90% of the particles emitted from diesel engine comes under PM2.5. And there is a problem with the small size particle. What we have already discussed. What is that problem?
it can it can go and sit at the
It
lungs.
is breathable. Yes.
Breathable. Yes, you're right.
Breathable. So there is something we discussed called settling time, if you recollect. Settling time of particles. Settling time of particles is inversely proportional to square of the diameter of the particle. So this is particle dia. So settling time is the time taken by the particle to settle down in the ground. So when we talk about the particulate emitted from engine, there are certain time period where the particles are suspended in air. After that period, it is going to settle down in the ground. Until that point of time, it is going to be suspended in air that we breathe. Right. The problem with long settling time is these particles are suspended in air when we breathe. We are taking in air along with the particle. This is where the problem is. So we have more health issues related to long settling time or with respect to small particle. And unfortunately, most of the particle, as I indicated here, more than 90% of the diesel exhaust consists of PM 2.5. That is particle size less than 2.5 micron. So in a typical range of 10 nanometer, that is 10 power minus 9 meter to 2.5 micrometer, that is 10 power minus 6 meter. So 90% of the diesel exhaust are having particles in this size, and these particles are going to be suspended in the surrounding ambience for longer time. When we breathe, we may take this particle along with the air. This is where the problem is. Okay, so we have these three categories of particulate matter based on the size. That is how they are classified with respect to size. And US EPA, what is EPA? EPA is Environmental Protection Agency. They are well known because these people set the emission standard, stringent emission standard, as being followed by many countries. So this Environmental Protection Agency located in US, they have given a definition for particulate matter, which is what I have reproduced here. So according to them, what is PM? PM is any substance other than water that can be collected by filtering diluted exhaust gas at or below 52 degrees Celsius in a dilution tunnel. So how they have defined particulate matter is they have defined based on control condition in a equipment. That equipment is called dilution tunnel. So this is a typical schematic of dilution tunnel. What this tunnel will have is a filter. This is the filter is Teflon material coated with fiberglass. Teflon coated fiberglass. I mean, it's a fiberglass material coated with Teflon. That's what is the filter, right? You have in this dilution tunnel of well-defined dimension. Basically, they are creating a control conditions to measure the particulate. That is what is happening in this dilution tunnel, and they have defined the temperature also at which this measurement has to be done. So when you allow diluted exhaust gas, what is diluted exhaust gas? Air with exhaust gas. So here you have air mixed with the exhaust gas that is coming out of the engine tailpipe. So you are diluting exhaust gas coming out of the engine tailpipe with air. Why do we dilute exhaust with air? Are there any reason? What reason? Is there anything you can think of? Hello?
Sir, to reduce the temperature.
Yeah, to reduce the temperature or to reach this control temperature. That is reason number one. So they have defined the temperature at which you need to collect the particulate matter. The temperature they defined is 52 degree. You know, exhaust gas temperature is going to be different based on operating condition, right? A different operating condition, you will have different exhaust temperature. Do you agree? When I say operating condition, speed and load, right?
Yes, sir.
So, so if you have to reach this control temperature, you have to mix gas with air, right? So, and the proportion of air you need to vary so that you can reach this 52 degrees Celsius. That's why you see that the dilution ratio, that is air to gas proportion, vary anywhere between 3:1 to 20:1. You have to add more air when the exhaust temperature is high. So this is the dilution ratio, that is air to exhaust gas ratio, 3:1 to 20:1. Either less air or more air depending on the actual temperature of the exhaust gas, because you have to bring it down to 52 degree. So what you are doing, you are mixing air with exhaust gas to reach this particular temperature. Dilution ratio is accordingly varied. And then this gas exhaust with air is allowed to pass through the dilution tunnel, which is a stainless steel tube of 30 centimeter diameter. And it has a filter with fiberglass coated with Teflon. Okay, so once you have a diluted exhaust passing through the filter, the material collected in the filter is defined as PM, anything other than water, right? Excluding H2O, any other substance collected in the filter is what is defined as PM. So we are collecting PM under this control condition by passing diluted exhaust gas through this filter at a temperature of 52 degrees Celsius. Accordingly, the air proportion is varied. Okay, and what we do is we will measure the mass of the filter before filtering and after filtering. Before filtering, you have a clean filter. After you pass the diluted exhaust gas, it will be deposited with the particulate matter, right? So the mass is going to be different. So PM mass is defined as the difference between the mass of filter before filtering and after filtering. That is what is the PM mass that you define by having this control condition and having an equipment called dilution tunnel. That is how you get an estimate of particulate matter mass that comes out of the engine cylinder. It doesn't give you any information about the size, but rather we get information about how much of PM mass is present in the engine exhaust. By having a diluted exhaust gas passing through this dilution tunnel with the filter, measuring the filter mass before filtering and after filtering, you will get an estimate of PM mass, particulate mass. So this is how US EPA has defined what a particulate matter is and how to get the estimate of PM mass by using this dilution tunnel. It's time up. I stop here. If you have any questions, you can ask.
Is PM10 contains all PM 2.5? Means PM10 is less, everything less than 10 micrometers, right?
No. What I said here is when I say PM10, it is from 2.5 micrometer to 10 micrometer. Upper size limit is 10. Lower size limit is 2.5. That is what is PM10.
Okay.
PM 2.5 is anything below 2.5 micrometer.
Okay, sir. Thank you, sir.
And this TPM, total particulate matter, is anything between 10 micrometer to 100 micrometer. Upper size limit is 100 micrometer. The lower limit is 10 micrometer. 10 to 100 micrometer is TPM. 2.5 to 10 micrometer is PM10. Anything below 2.5 is PM 2.5.
Sir, one question I want to ask is that undermixing is one of the phenomenon by which we are getting SC in CI engine.
Yeah, yes.
Right, sir? So basically, sir, undermixing is when the time is not available for the mixing at all.
Yeah.
So by calibrating the engine in a proper way, we can completely avoid this phase. Or
you cannot avoid, because you cannot avoid diffusion combustion, right, in conventional mode. What I mean to say here is it depends on the duration of injection. You continue to inject even after start of combustion, right? That's why one of the question I asked in quiz 2 is mark the end of injection. End of injection is always after the start of combustion. So whatever fuel you are injecting after the start of combustion, there is no pre-mixing here. It is like instantaneous mixing that should happen.
Got it, sir. Got it, sir.
So you cannot avoid undermixing in a conventional diesel combustion. Later on, I will talk about completely pre-mixed diesel combustion. That is one of the my research area of interest currently, and we completely eliminated diffusion combustion. By eliminating diffusion combustion, you can overcome this problem. In fact, we can get very low NOx and very low soot. I will discuss about that later on.
Thank you so much, sir.
Okay, fine. So I stop here. We'll meet tomorrow at 6 o'clock. Thank you.
Hello. Hello,
Yeah.
sir. Good evening, sir.
Yes, yeah.
Sir, I joined little late. Vijay Raj.
Okay, you joined late. Okay.
Thank you,
So
sir.
Rahul is joined.
Yes, sir. He's in the call, sir.
He has also joined.
Yes, sir. We joined, sir.
Am I audible?
Yeah, yes.
Yes, sir. Yeah.
Okay. Okay, I have more.
Yeah. Thank you, sir.
Yeah.
Thank you.
So I'll stop here. I'll meet you tomorrow at 6 o'clock. Thank you. Bye.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you.